In this example, we're going to be titrating a strong acid with a strong base. Specifically, we'll be titrating a 50 milliliter sample of 0.1 molar HCl with 0.1 molar NaOH. And you can see that there's a graph in the middle of the screen with pH units on the y-axis representing the pH of the solution in the beaker. And the x-axis is measured in units of NaOH added, so milliliters of NaOH that are added to that acid solution. And hopefully as we add more base, we should see the pH begin to rise. And we'll plot a pH curve by calculating the pH at various points along this titration. So at 0 milliliters of base added, the pH is just the pH of the acid solution. So we have 0.1 molar HCl, and HCl dissociates 100%. So we have 0.1 molar H plus ions effectively. So the pH before we add any base is just 1. Things get a little bit more interesting once we start adding base, however. So we'll do a couple of calculations. First one is when we've added 10 milliliters of base, and then the second one is after 20 milliliters of base. So in each calculation, we're going to have to start with the amount of HCl that we have in the first place. So we have 50 milliliters of 0.1 molar HCl, and that's effectively 0.005 moles of HCl. We're adding 10 milliliters of 0.1 molar NaOH. That's the same as adding 0.001 moles of NaOH. And at this point, the reaction hasn't happened, so there's no H2O or NaCl in the solution. In this example, HCl plus NaOH is a 1-to-1 reaction, so we can just subtract the amount of NaOH from the amount of HCl. If you wanted, you could also do this with mole ratios like we did in Chapter 3. Now this might look like an ICE table like we've done in chapters 15 and 16 and some in chapter 17 as well, but it's important to recognize that this isn't an equilibrium situation. This is a one-direction reaction situation. So this is just straightforward stoichiometry. And we can see that after the reaction happens, there's no more NaOH, and we've got some leftover HCl and a little bit of sodium chloride and water produced. So the NaCl doesn't affect the pH, water doesn't affect the pH, and really all we have to do is look at the HCl concentration and calculate the pH with it. Now the trick is we've added a bunch of base solution, so the volume's changed. We started out with 50 milliliters of HCl, we added 10 milliliters of base, so we have 60 milliliters total. And if we do the pH calculation for the H plus ion that comes from HCl, we can find that the pH has gone up to 1.18. So not a very dramatic change at this point. It's still mostly a solution composed of HCl. Very little change. In our second calculation, we'll look at what happens after 20 mils of NaOH have been added. So HCl, the initial solution, still contained 0.005 moles. That's what we started with initially. At 20 milliliters of added NaOH, we have 0.002 moles of NaOH that were added. And again, initially, NaCl and H2O are effectively 0 for this reaction. And then we can find out how much of each reactant and product is left over after reaction. And again, after the reaction, we find that all of the NaOH is used up and some NaCl and water are produced. Primary component affecting the pH is still HCl. And we can calculate the pH of this new solution exactly the same way as we did earlier. We find the new concentration of HCl and we find the pH directly. If you do this math, what you'll find is the pH is equal to 1.37. Again, has not gone up very dramatically. It's a slow and steady increase in pH. At the equivalence point, this is the point where we've added enough base to stoichiometrically use up all of the acid. In the case of a one-to-one reaction, this is when you've added the same number of moles of acid as base. And what you can see is at the end of the reaction, all of the HCl is gone, all of the NaOH is gone, which is what you would expect at the equivalence point. Both of the reactants have been used up completely. The only thing in solution now is NaCl and water, neither of which are going to alter the pH. So the pH for this solution at equivalence is effectively just the pH of pure water, which is to say 7. And because our concentrations of HCl and NaOH are equal, and it's a 1-to-1 mole ratio, this must happen at the 50 milliliter mark. And as we add more base, even after the equivalence point, the pH continues to increase. In the next example, we'll look at what happens after we add 70 mils of NaOH. At 70 milliliters of NaOH added, we've added 0.007 moles of NaOH. At this point, our HCl becomes limiting, it runs out, and we're left with some leftover NaOH as well as NaCl and water, which don't affect the pH. What we can do now is work out the concentration of NaOH. So we would do the same thing as we did with the HCl. We look at the moles of NaOH, we divide it by the total volume of solution, and we get a concentration. We can find the pOH, and then we can find pH using pH equals 14 minus the pOH. And if we do that, we'll find that the pH is 12.2. And if we wanted to go through this and work out what the pH was at every single individual iteration, every single point on this x-axis, we could, but instead I'll just draw the graph. You get a curve that looks something like this. You get a long, steady increase in pH before the equivalence point. At the equivalence point and just around it, you have a very, very sharp increase in pH. And after the equivalence point, you have a slow, steady increase in pH. Now this is for a strong acid with a strong base. If we had switched the example and we were titrating a strong base with a strong acid, the graph would look pretty similar, but it would be flipped over. We would have an example that starts at high pH because a strong base is going to have a high pH, and there would be a slow and steady decrease in pH. And then there would be a sharp decrease at equivalence, and then there would be a slow and steady decrease afterwards. So it would look pretty much the same, but inverted. So we can do an example of a strong acid and base titration, very much the same as the one that we just did. We can look at the titration of 25 milliliters of 0.2 molar HCl with 0.1 molar NaOH, and we can calculate the pH of the reaction mixture at 4 different points. Initially, after 25 milliliters of base are added, after 50 mils of base are added, and then at 55 milliliters of added base. So initially, for A, we have 0.2 molar HCl, which means 0.2 molar H+, which means we can calculate the pH directly. And we get a value of 0.699. B was after adding 25 milliliters of NaOH. And in this example, we have to decide how much acid and how much base are left over. So we look at our initial amounts of acid and base, and then we can decide how much is left over. And we see that after this titration has happened to this amount of base, we have no NaOH left over. We have NaCl and water, which don't contribute to the pH, and we have 0.0025 moles of HCl left over. We divide that by the total volume. So we started with 25 milliliters of acid, added 25 milliliters of base. That's 0.05 liters. And we can calculate the pH. And we get 0.05 molar. And the pH of that is 1.3. So our pH has gone up, but not considerably. The next example happens at 50 milliliters of base added. And again, we're going to do the same kind of math. And we can do this explicitly, but at this point you've seen the pattern, and I'll just give you the pH. The pH is 7 because we've added equivalent numbers of moles of NaOH and HCl. For D, this is 55 milliliters of base. In this example, we're going to be adding 0.0055 moles of NaOH. And in this case, we have base left over, NaCl and water that don't do anything to the pH, and we can just calculate our OH minus concentration. We take the number of moles of base, we divide it by the total volume, and we get our concentration of NaOH, which we can use to find the OH minus concentration. It'll be the same thing because they exist in a 1-to-1 mole ratio. And we can calculate the pOH. And it's effectively 2. 14 minus the pOH gives you the pH, and 14 minus 2 is 12, so the pH is 12.